Welcome to lecture 17b on bases and dimension for vector spaces, part B. Recall that a subset of a vector space is a basis for the vector space if every element of the vector space V can be written as a linear combination in exactly one way. The dimension of a vector space is the number of elements in any basis. For example, the dimension of Rn is n. We have the standard basis consisting of n elements, or you can also think that you need n entries to describe a vector of height n. The vector space of all polynomials has the standard basis. It has infinitely many elements, so this vector space is infinite dimensional. The subspace of polynomials of degree n or lower has n plus 1 entries in the standard basis, so the dimension is n plus 1. We have talked before about the relations between spanning sets, linearly independent sets, and bases for Rn. Now we will generalize these relations to finite dimensional vector spaces. Suppose I have a vector space V which has a finite dimension. If I have a spanning set for V, then I know that I can make a basis out of the spanning set by possibly removing some elements. This is the same situation that we have before with vectors. We learn a Dirac algorithm to find this basis, and this also works in general. If I have a linearly independent set in V, then I can add enough elements until I get a basis. And for this one, there is no general algorithm. Thanks to this, I can say the following about the connection between the dimension of a vector space and the number of vectors in these special sets. So I know that every basis for V contains exactly dimension V many elements, but I also know that every spanning set for a vector space contains at least dimension V many elements. And if it's equal, then I have a basis. Every linearly independent set in V contains at most dimension V many elements. And equality implies it is a basis. This only works for finite dimensional vector spaces. If the dimension is infinite, equality in this case does not imply a basis. The 2 out of 3 rule, which we saw before for vectors, also applies here. If I have some elements in V and assume V is a finite dimensional vector space, if I know that 2 of the following 3 conditions are true, then I know the third is automatically true. So for example, if I just know that 2 of these are true, then I know that my elements form a basis for V. This is most useful if you already know the dimension of the vector space and you want to check if a subset T of V is a basis. We can first compute the number of elements in T. If the number of elements in T is the same as the dimension of V, then we only need to check one of these 2 conditions, either spanning or linearly independent, and one is usually easier. Here is another theorem which generalizes vectors to elements of a vector space. Again, if I work with a finite dimensional vector space and I know that W is a subspace, then I know that the dimension of W is between 0 and the dimension of the bigger vector space V. If the dimension of W is 0, then W has to be the 0 subspace, the subspace consisting of just one element, the 0 element. If the dimension of W is the same as the dimension of V, then W must be the entire V. In this exercise, I am working with P2 and let V be a subspace with the following properties. I don't know what V is, but just using these 3 clues, I want to find the dimension of V using what we had just seen in this slide and previous slides. First, I know that the dimension of p sub 2 is 3. So by this theorem, v has to be either 0, 1, 2, or 3. I will now check each possibility. Let's first look at the possibility of having dimension 0. This says that if the dimension is 0, then the subspace must be the 0 subspace. But the first clue says that I have a polynomial, which is not the 0 polynomial, being in V, so V cannot be the 0 subspace. Because we have a non-zero polynomial, this one, being in our subspace, this means V is not the 0 subspace, so the dimension of V is not 0. The second clue says that I have a polynomial which is in P2 but not in V. This tells me that V is not the entire P2. We're told that there is a polynomial in P which is not in V, so V is not the entire P2. The theorem on the previous slide tells us that in that case, when the subspace is not the entire space, the dimension of the subspace must be smaller than the dimension of the entire space. So the dimension of V cannot be 3. The only two possibilities left are 1 and 2. We also have one clue left that we have not used. It says that our subspace contains a non-zero polynomial P where 3 is a root of P. Clue A and C tell us that we have at least two non-zero polynomials in V. If we can show that these two polynomials are linearly independent, then we can use theorem 1 to say that the dimension of V is 2 or bigger. I claim that this polynomial and x squared minus 1 are linearly independent. To show this claim, I first write an arbitrary linear combination of p and x squared minus 1 and set this to 0. From clue C, I know that if I plug in 3 into p, I should get 0. So let me plug in x equals 3 into this equation. Clue C tells us that this term is equal to 0. This means that C2 times 8 is 0, so C2 has to be 0. I will now put this back into this equation. This tells me that C1 times P of x is 0. So either C1 is 0 or P of x is the 0 polynomial. But the clue says that P is a non-zero polynomial. So this isn't true. So it must be that C1 is equal to 0. We now have C1 is 0 and C2 is 0. And we started with this assumption. So the only linear combination where this is equal to 0 is where C1 and C2 are both 0. This tells us that these two elements are linearly independent. Since this set is linearly independent, the theorem from a previous slide tells us that the number of elements in the set, which is 2, is less than or equal to the dimension of V, but we know that V is not the whole space P2, so the dimension is smaller than 3, and so it must be 2. In this exercise, even though we are not given a concrete description of V, using logic, we were able to determine the dimension of V. In a previous lecture, we showed that the following set S, where S is the set of polynomials, where f of 5 is equal to 0, is a subspace of P sub 2. We will now use the theorems we just learned to find the dimension of S and then find a basis for S. Finding the dimension of this subspace will be very similar to the previous exercise. We know that the dimension of P2 is 3, so the only options for the dimension of S are 0, 1, 2, 3. To show that the dimension is not 0, we only need to come up with one element in S, which is not the 0 element. The polynomial x minus 5 has a root at 5, So if you plug in 5 into this polynomial, you get 0. So this polynomial is in S, and it is not the 0 polynomial. So we know the dimension of our subspace is not 0. To show that the dimension is not 3, we just need to show that there is one element which is in P2, but not in S. For example, I can take x squared minus 1 because 5 is not a root of this polynomial. Another option I can use might be the constant polynomial 1. The root of that polynomial is not 5. So S is not the whole P2. So the dimension of S must be smaller than the dimension of P2, which is 3. To show that the dimension of a subspace is 1 would be to show that every element in that subspace is a scalar multiple of some other element in the subspace. And to show that the dimension is 2 would be similar as last time. We need to come up with 2 elements which are linearly independent. Let me think about possible elements in S. I know that x minus 5 is in there. I can also find a quadratic polynomial which has 5 as a root. For example, x minus 5 squared would be in there. So let me check if this polynomial in x minus 5 might be linearly independent. I can do the same process that I did in the previous exercise, or I can observe that x minus 5 is not a scalar multiple of x minus 5 squared, because this one has degree 1 and this one has degree 2. And x minus 5 squared is also not a scalar multiple of x minus 5. So these 2 polynomials are linearly independent, and we can apply the same logic that we did in the previous exercise. Theorem 1 tells us that every linearly independent set in a subspace contains at most dimensions of the subspace many elements. Since the dimension of S is smaller than 3, we have the following inequalities, and so the dimension of S must be 2. Now that we know the dimension of S is 2, we will use this to find a basis for S. We already computed that the dimension is 2, and we already have a subset which is linearly independent, and the subset has the correct amount of elements, the same as the dimension. So we are in a good position to use the 2 out of 3 rule for vector spaces. With this rule, if we know that a subset is linearly independent and the dimension of the subspace is the same as the number of elements in this set, then we automatically get that the set is a spanning set, and that's exactly what we have. Since our set satisfies 2 out of the 3 properties, we know it is linearly independent, and we know it has the same number of elements as the dimension of S, which is 2. So the 2 out of 3 rule tells us that this set is also a spanning set for S. By definition of bases, then this set is a basis for S, since it is both a spanning set and is linearly independent. We have been talking about general vector spaces for a while. Let us now go back to the world of vectors. In fact, we can use bases for general vector spaces to convert elements in a general vector space into vectors. And this is nice because many of the tools from this class involving vectors are tools that are easy to compute either by hand or with a computer. If I have a basis for a vector space V and I have an element in V, the coefficient vector of that element in the basis B is defined to be this vector where the entries are the coefficient in the unique linear combination of my basis elements for W. The coefficient vector records the list of coefficients of the unique linear combination equal to W. For example, let's consider the vector space P4. We have the standard bases of P4 consisting of these 5 elements, and this polynomial is an element in P4. Let me now write down the coefficient vector of this polynomial in the bases, in this basis. First, I need to write down this polynomial as a linear combination of the bases, and I've done that here. Now I will just look at the coefficients and take them to be the coefficient vector. So my coefficient vector is just this vector of height 5 with entries 5, 0, 1, 0, 0. Once we have a basis for an n-dimensional vector space, every vector in Rn is the coefficient vector of a unique element in our vector space. This is really nice because this allows us to translate problems in abstract vector spaces or just other vector spaces into problems in Rn, which is much easier to think about and compute. Instead of thinking about bases or linear independence or spanning sets in a general vector space V, we can just think about these sets in Rn. If I have a basis for a finite dimensional vector space, then a set of elements in V is a spanning set for V if and only if their coefficient vectors is a spanning set for Rn. If I have a set of elements in V, that set of elements is linearly independent in V if and only if their coefficient vectors are linearly independent in Rn. A set of elements is a basis if and only if their coefficient vectors form a basis in Rn. So instead of thinking about the elements in V directly, we can just work with the coefficient vectors. So we don't have to work in V, we can work in Rn, which is much easier. Let's apply this to this exercise. Let W be the subspace of C infinity, the vector space of all smooth functions, where W is the span of this set e to the x and e to the negative x. Instead of thinking about the elements of W as being smooth functions, let's now use the coefficient vectors. Our subspace is defined here to be the span of e to the x and e to the negative x. So by definition, this set is a spanning set for W. To show that this is a basis, we just need to show that it is a linearly independent set. But this was something that we showed last time. So we are done. We have shown that this set is a basis for W. Since this set is a basis for W, we can write any element in W as a linear combination of e to the x and e to the negative x. I will write down a formula for the hyperbolic sine and hyperbolic cosine in terms of e to the x and e to the negative x. And from there, we can easily compute the coefficient vectors of these two functions. Recall that the hyperbolic sine can be written in this way: e to the x minus e to the negative x divided by 2. Hyperbolic cosine can be written as half of the sum of e to the x and e to the negative x. Once I write them this way, it is clear that 1/2 and negative 1/2 are the coefficients for hyperbolic sine in the bases of e to the x and e to the negative x. So the coefficient vector of the hyperbolic sine is 1/2 and negative 1/2. The coefficient vector for the hyperbolic cosine is just these two coefficients here. So I have 1/2 and 1/2. Note that the fact that you can write these two functions as linear combinations of e to the x and e to the negative x tells me that these two functions are in my subspace. Now that we have that these two functions are in W, and we also have their coefficient vectors, we can now show that this set is also a basis for W. We will use this statement. We can say that a set of elements in a general vector space is a basis if we can show that their coefficient vectors form a basis in Rn. In this case, we are just working with R2. Because this set consisting of two elements is a basis for W, we know that the dimension of W is 2. And so if we can show that a set of two coefficient vectors is a basis in R2, then we know that the corresponding elements form a basis for W. So we just need to check that this set of two vectors is a basis for R2. To do this, we just need to verify that this set is linearly independent because we can apply the 2 out of 3 rule since we know that the dimension of R2 is 2. To show that this set is linearly independent, we take the concatenation matrix and we need to show that this concatenation times a necessary vector equals the 0 vector has one unique solution, which is that both variables are 0. I turn this into an augmented matrix and row reduce. I multiply both rows by 2. And now I have this leading one, and I will kill the entry below. And I arrive at a row echelon form. I see that every column to the left of the vertical line has a leading one. This shows that this equation here has one unique solution. So our set is linearly independent, and by the 2 out of 3 rule, we have that this set is a basis for R2. Going back to here, this tells us that the set of hyperbolic sine and hyperbolic cosine is a basis for W. Since the coefficient vectors of hyperbolic sine and hyperbolic cosine form a basis for R2, we can say that our set is a basis for W. And we know that because the dimension of W is 2. So what we have done here is without even working with C infinity, we were able to conclude something about a subspace of C infinity by using the power of coefficient vectors. One of the reasons why we work with vectors in linear algebra is because we're able to apply tools of vectors to other situations that don't look at all like vectors, like in this case. This is the end of lecture 17b. Thank you for listening.